That's very nice. Yeah, I don't do that. But not here, really.
The answer should be no.
Oh no.
My answer.
Must be a social sometime. Unfortunately, this February and March are out for me and also for you, so it becomes easy for me, doesn't it? I can't think why, but it's something to do with me. Yeah, I won't be able to get there. Teaching my French. I saw. Good luck. Yeah. They're very busy, so that's exciting. See you.
I guess you're not used to wearing them, are you? We're not used to. I suppose I think everyone else gets used to wearing them because they play like you see very better weather.
Okay, so please remember to log in on the DLE. video. Good. Yeah, that's good. I'm just about to lecture, so let me show you my team. There you go. Where are you? Thank you. Good. So log into the DLE, please, and we'll spend an hour looking at some of the ideas, and then the second hour will be using Qt and doing some software.
Κάτσε. Λοιπόν, εγώ ξεκινήσω να το γράψουμε. Αυτό πώς να κάνεις. Γιατί δεν παίρνω. Ναι. Έχεις πετάξει έξω. Α, το δάμε, ωραία.
So we've looked at biology, we looked at MAR and other models and cameras and edges and a little bit of shape and moments. I want to now look at texture and other shape descriptors and how people use these for tracking targets. Then next week we'll look at active vision from a model by David Ballard, and then we also next week, next Wednesday, we'll look at stereo vision, and we will certainly need to be doing the OWL then. Now, one person emailed me about trying to get an OWL. Who was that?
Yeah.
Were you successful?
Yeah.
Good. Okay, so between now and next Thursday, you all must sign out your own, well, in pairs, remember, you're working in pairs, because notionally there's supposed to be 10 of you here.
I guess I can use mine for like with my friend, right?
You can, of course,
Yeah.
yes. Yeah. And you are responsible for these robots, so please don't lose them or allow them to be stolen. Now, first, something that is important, and this is the point of sampling of the image. So the camera has some properties that you don't really know about that you need to account for, or may need to account for. And it all comes under the general heading of camera calibration. A camera has a sensor and it has a lens on it. And the lens is responsible for distortion, and the placement of the camera behind the lens also affects the quality of the picture. So you need to know several things about the camera, sensor and about the lens in order to correct for those things, so that the picture you take is then standard. So that if you take the same picture with another calibrated camera, you should get the same results if they have the same field of view and they have the same position and same lighting conditions. So we need to worry about the sensor position, which is a 3D pose of the camera sensor sitting on the printed circuit board behind the lens. We need to worry about the distortions of the lens, and those come in. There are two types of distortion. There's pincushion distortion and chromatic distortion. Pincushion is due to the edge of the lens giving you more distortion than the center. It's inevitable in cheap lenses, so plastic lenses usually have a very high amount of pincushion effect. And chromatic distortion is due to the way in which the lens treats different wavelengths of light and how they bend to hit the focal plane. So there are 4 intrinsic parameters for the 3D geometry and 5 distortion parameters for the for the distortions. And there's a standard calibration process that can be used to define these parameters. So looking at this schematically, this is the sensor plane, this is the object, and somehow the object is rendered through the lens into a coordinate system that is represented by the sensor. And the distortions will affect the location of every point of sample of that object on the camera frame. We don't notice these things, but those of you who wear glasses will notice that when you take your glasses off, a square screen will appear cushioned in, and then you put your glasses back on and it all looks happy again. You take your glasses off, you forget about wearing them for a couple of hours, and you look at the screen again and the screen now looks square. So you've automatically compensated for your vision system. We need to do that for the camera. Now, typically this is done with a checkerboard pattern, and we used to have one here. I haven't seen it this year. I meant to bring one. I'll get one made up so that we have it here. And it's typically a A4 piece of paper with a checkerboard on it. Inkjet printed is sufficient, and you stand in front of the camera and hold the checkerboard in different poses around the approximate distance for sharp focus, and in doing so you have a bunch of pictures which typically might be a minimum of 9, typically maybe 20 of these pictures, and the software will then analyze these pictures, and knowing that there are 1, 2, 3, 4, 1, 2, 3, 4. So that's a 4x4 checkerboard pattern internally here, that it will make assumptions about the evenness of the checkerboard when printed, and then adjust the camera calibration matrix to correct for the non-linearities that it measures when it analyzes all of your calibration pictures. So OpenCV has a standard calibration process. In fact, there's several people who have written camera calibration code, and it's freely downloadable, and it's available in the samples folder on each of your machines in the OpenCV samples folder. And here you can see it's just mapping and drawing the corners. The reason why it uses corners is because corners have an X and Y component to them that can be monitored. A straight line in the X direction only has a Y component, and a straight line in the Y direction only has an X component. So the corner has both an X and a Y component. You can see the effect. This is a picture on the left taken with an uncorrected camera, and this is the corrected version of it. Now, this is a low resolution picture, but you can see here that this window ledge is nicely curved because it is spanning quite a large visual angle in the camera from far left to far right. You look at the computer here, and to our eyes that looks reasonably straight, but if you then reproject the picture to be corrected for the lens and lens distortions, which often make up the major parts of this error, you can see there that is straightened, and that now is also straighter, although the error is very small here. Notice that in straightening we lose information down this side due to the way the projection is only looking at the calibrated part of the picture. And this is tessellated because it's low resolution, but you would get that same tessellation, albeit very finely, if you had a high resolution camera. So why would we do this? Well, if we want to calibrate our scene, then we need to do that. Let's imagine we've got a security camera. It's standing on a pole down Union Street, looking across people drunkenly walking around Union Street. They know where the camera is in terms of 3 dimensions. They will know where the surface of the pavement is, so they will know any particular angle will be giving a line of sight to a certain distance away. So if they're trying to estimate the height of a person, it will be smaller farther away, and closer it will be the height will be larger. If it's non-linear because the camera is not corrected, then the calibration procedure will be non-linear. However, if you linearize it here, then the distances will be more linear and more reproducible, especially if you change the camera because that one malfunctions and you have to put another one in. If you had an uncalibrated camera system, you would have to redo the measurements. With a calibrated camera system, you just have to recalibrate the camera using the checkerboard, and then you can place it up there and all the measurements continue to operate. Okay, so let's assume we have a calibrated camera. Let's extend our exploration into features, looking at edges, corners and textured patches. And we've got a choice that which ones we use according to the computational load on the computer, the resolution of the picture, the number of features that we are going to be dealing with. Really places quite a heavy burden on the computer. But we can use edges, corners and textured patches to describe shapes, to describe objects, to track objects in motion, and to also estimate distances by finding edges, corners or textured patches that correspond between the left and the right camera, or indeed if you have multiple cameras, because in principle you can have as many cameras as you like in a stereo view. As long as the mapping between each camera is known, you can then reconstruct the views. Now, there are many problems with edge detectors, and one of them is that it's very difficult to establish correspondence, and the word correspondence is often used as a posh word for matching, because the edge throws away a lot of information. We only record the centre of the edge and the strength of that edge. So you're trying to match strength and edge position across cameras or across time as a target is moving. Have a look at the Susan edge detector for a critique on edges and their problems. But as I said a moment ago, with this picture, the trouble with edges is that you do not have two-dimensional tracking capability. This edge, if that edge moves in that direction, then you can track it in the X direction, but if it moves in that direction and you are monitoring here, you won't notice any change at all. It's only when it becomes a corner that you will notice the change. So we generally track corners as the simplest possible feature to monitor. So corners are defined as regions of high contrast or curvature. We calculate the second order derivatives of the corner. There are two popular methods, one due to Harris and one due to Shi and Tomasi. We create a Hessian matrix output, and as a result of this, we can track those corners. Here's an example for a Harris. We can use OpenCV or MATLAB. It's not rotational or scale invariant, so if the corner rotates, the numbers you get out change. So let's look at some corners in two separate scenes. You can see that the door has changed position between those two. This is the sort of information you're getting around a small patch around each of the corners that the machine has chosen. So you can see that there is an essence of a corner there and there, not so much there, but there appears to be enough for the machine to resolve, and also there and there. So we've got enough to measure a two-dimensional motion. If we take these corners here and those corners there and then do a cross correlation of them all, so we cross correlate all of these patches for the left and right pictures, this is the cross correlation. So there were 5 patches, and if you correlate it with itself you get a good result. So if you can find it, then you get those results. If you match with another patch that is not the same one that's moved, then you get a lower correlation, and you can see that the correlation scores vary quite enormously. The method of matching is therefore statistical. On balance of opinion, we think there's a match. And we will use that as our guess as to where the corner moved to. So in this simple scene, we're getting quite strong matches. 96%, 75% sure, 77, 78, 98% sure. And then the expected non-matches are all less than 50%, so 48%, 39, 51%. So you can see that there's kind of a gap between the probability of it being a good match and the probability of it being a bad match. That gap will reduce the more features that you have that you're trying to compare. So if you had a bigger picture and there were multiple things moving in the picture, there would be a point where only the strongest matches will show through as being easily seen, and all of the other ones will just be in the noise, and you will never be sure whether it was a good match or a bad match. So using corners is something that doesn't scale particularly well, but it's used in most navigation schemes at the moment because it's cheap to do computationally. The Sheehan-Tomasi detector is in OpenCV is called Good Features to Track, and I have a feeling that I've included the paper on that in the papers section, so you can read up about how it operates. You can see it's actually got a lot of you're passing a lot of parameters. There's 2 parameters. The image. Yes, the input image, the eigenvalues image, which is the calculated edges, and a temporary image to do some calculations in, and then a set of corner locations. So we've scanned the picture looking for corners, we find the number of corners, we have some quality level. The minimum distance is the expected minimum position change between 2 pictures, and I'll talk about this in a moment. You're choosing a size, a kernel size around which to check for correlation. We can choose whether you use Harris or not in this, and we generally don't use Harris, and this is another quality function. So there's a number of things that you have to set by hand, a number of working directories, and the issue is all around the number of corners and the size of the corner. So if we just go back to here, we can count here, and we can see, I can see 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Yeah, these are 7 by 7 matrices. So we've taken a 7 by 7 patch around the corner, and we're correlating a 7 by 7 function. Now, a 7x7 gives you 49 different pixel values to correlate. So you have to correlate 49 of those against 49 of another one. If you have 3x3, then you're only correlating 9 pixel patches. If you're doing 5x5, then it's 25. You always use an odd value, and there's a balance to be made between choosing a small patch which won't be resilient to noise, because you will find lots of other patches that actually will have a similar correlation but won't move, or won't be the same corner. Or a large one, you could maybe go for a 21x21, but then you run the risk, because you're doing this blindly, you run the risk of taking in some background sample that doesn't move. If this is a target that's moving over a background, then the larger the patch, the more background you're trying to correlate with the actual corner. Okay, so I want you to look at corner detection. I want you to use the Sheehan Thomasson detector so that you can understand how corners work. Thanks to GPU computing, it becomes easier or cheaper computationally to use texture patches instead of corners. So a texture is defined as a locally repeating spatial or temporal pattern. There's some links to review what texture is here. Rogat's created a reference set of textures, and you will see in the machine vision community, people declare public databases full of standard things that others can use to compare performance of algorithms. Rogat produced a list of textures of everything from bricks to pebbles to grass and trees. So he did a very extensive exploration of texture. And this was before high-speed texture processing was possible. So he was just doing this to establish the principles of texture analysis. A technique that's quite common in GPU processing and deep learning is to use Gabor analysis for texture filtering, and I'll show you that in a moment. The Gabor filter can be tuned to extract texture parameters. You can use Fourier analysis as well. What you do is you convert the target patch into Fourier space, which analyzes the patch for frequency components, and that histogram of frequency components then is the texture descriptor for that patch. And again, you can look at how that's done from the papers. So, whatever method we're using, we detect features and then track them between different pictures. So with a stereo picture, it's going to be a left and right image. With a motion picture, it's going to be a snapshot in motion. But you will also come across people working what's called long baseline stereo, which is where you want to navigate around a town, let's say, and you want to know how far you are from one particular scene, and you are going to maybe make sparse samples through the town. The problem in drawing correspondence lines, so linking every corner to every matching corner, is that the search amongst corners is not unique, as I suggested from the Harris example just now. And somehow you've got to discern things that you want to search for. So landmarks, for example, if you're doing a navigation problem, you don't really want to be searching for something that moves. You want to be searching for landmarks that do not change, and those may be things that are far away from you rather than being close to you. So there's a considerable amount of feature assessment that goes on inside computer vision tracking algorithms to decide whether or not that feature is robust enough to use. Those of you who understand Kalman filtering will understand that Kalman filtering is often used to decide which features are going to be useful and which ones are not, and how to project your map points forward in time. The good thing about using Harris is that it's fast, it's good enough, provided your camera stays upright all the time, it's good enough to allow you to estimate self-motion. Now, I said that corners are not reliable, but they are cheap to do computationally. There are lots of detector techniques. I mentioned Susan as being an edge detector. It's actually quite a sophisticated multi-scale edge detector that has been used quite reliably to process features for tracking purposes. Patches is something that I mentioned briefly, texture patches. People are also using the SIFT algorithm, which is a scaling variant feature transform, which uses borrows from David Marr's ideas about the difference of Gaussian filtering, and if you remember that cake with little vector arrows on it, that the SIFT algorithm actually constructs for every feature that it determines to be valuable. It constructs a little vector diagram that is invariant to scale, translation and rotation, and then uses that to detect the same thing elsewhere in the picture or in another picture. This is the SIFT detector. It's quite an old idea. Let's see if we can get this running. Oh no, that's the demonstration point. So here, not very clear, but here you can see this is a monochrome picture, and this is the target, and we're showing the camera a scene, and it is trying to track that target. You can see that there are multiple features that it's trying to track. There's one feature in here somewhere that is erroneous, and it's decided it's down here, but by far the majority are very tightly arranged around the target, which is found here. So you can see there's some sort of picture with some writing. There's the picture and writing at a different scale and a different pose, three-dimensional pose. Using SIFT is has some limitations, but it's very robust within its constraints. The problem is that David Lowe and the university works for patented SIFT, so if you try and use it commercially, they will extract a royalty from you. There are, however, a number of royalty-free packages that do something similar to SIFT. Which brings me to a point about OpenCV, that there's a library that you download that we have on these machines, which is non-copyrighted, it is copyrighted, but is royalty-free for use. And there's also there's a non-free library as well, and SIFT is in that non-free library. So what happens is that we have a multi-scale difference of Gaussian filter. So multi-scale is an image pyramid, and it locates key points, and the key points we call local gradient orientation. So this is very reminiscent of David Marr's difference of Gaussian stuff. It rejects edges. So I mean, let's see what shirt I've got on. Oh yeah, this is a good one. So this is a texture, and it's a repeating texture. However, there's an edge around here where my boundary is. So if you are going to try and make a robust texture detector, you want to work out where the boundaries are of that surface so that you do not take samples from anywhere near that boundary. Because if you take a sample here, then you're going to be sampling, as I said earlier, some of the background, which is going to be random compared to you. So you only sample from within your surface and not at boundaries of surfaces. So the SIFT detector actually also does edge detection, and if there are any strong contrast edges, it does not try and take a SIFT kernel from around that region. So it only ever looks in the centre of the surface. And it then generates a hierarchical set of key points, one for low resolution pictures and one for high resolution, for low through to high resolution pictures, so that the target can be far away or close by, and you will find a match somewhere in the vector of SIFT descriptors. I think the SIFT descriptor is something like 160 elements long. So you're looking for matches across the scales. Let's just say, for argument's sake, there are 4 scales in that 160. That means that there are 40 vector points that you are comparing across those scales. So here's an example, a picture with some key points. And here you can see the key points are overlaid with the major vector arrow coming out of that key point patch. Some of these are large key points. You can see here this is a low resolution key point, and the vector arrow is that way, and that would be perhaps processing an area about that size, and giving the key point at the centre of that patch. Whereas some of the others are very small, and so the key point being processed in that area will be a small patch. You can process in colour. Remember, colour comes from the camera mostly in red, green and blue. So we've got, this is in micro with the colour overlay. So we'll look for little toy trains, a toy frog, and we find, let's see, I'm too close to that. We find the toy train here and here. I guess the frog, there are aspects of the frog there behind, hidden here. So you can see that there are parts of the frog, you see the eyes there, that are matching. So it can handle partial occlusion as well, because of the way in which the model's built up. We've looked at feature extraction, and we have, at least on the board, seen clustering, so that you will find features that are similar, and you then cluster those features, and that then allows you to compare clusters against an existing model. So the model, for example, could be that door used in the Harris example. We have a model of the door, forget that one, and the model of the door is rather poor with the Harris detector with the parameters set as they are. We've only got 1, 2, 3, 4 key points that model that door, but that's sufficient to start, so that we can then start looking for that door again, or find similar doors, and we may find those 4 key points. What you're looking for really is perhaps 100 or 200 key points around that target, which is what you get with the SIFT detector. So you get lots of key points, and you can
you then have a rich set of key points that you can use to determine whether you've seen that object before or not. And for example, in here, you can probably take a different perspective transformation of that and get a good match. There's probably 200 key points in here. You'll probably get a good match on 150 of them. That will then possibly be deemed to be sufficient to say, yeah, we've seen that picture before. Same in this one. There's going to be 20 or 30 key points in each of these that gives us enough confidence that we found something. If you only find one key point, then you probably just, one or two key points, you'll probably reject that as being noise. So we can match to an existing model. And that works, and people use that as a technique. But let's try and go one step further. We don't know what our existing model is. So what we're going to do is we're going to generate a model from data that we are collecting. So here, we're just now going to take lots of pictures of street scenes. And we're not going to label those street scenes. We're just going to take pictures of the street scenes and tell the computer that in each of these street scenes, according to the scene, there's a car, there's a person, there's a bus, there's a bicycle, there's a horse, and so on. And then for each street scene, you say what combination of those you have in there. The features are extracted, and they are then correlated statistically with the data that is coming from the streets, from the scenes, and you then build up your own model with each of those parameters, each of those targets accruing some statistical proportion of the features that are in the field of view. You can draw boxes around them to save yourself time, but if you're trying to do this to the current state of the art, you don't draw boxes around them, you do all of this just using Bayesian statistics. Each feature is then extracted, put into a bag of words. So it's a bit like sorry. So you have a bag and you throw each of these descriptors into that bag, and you then use those descriptors, that closed set of descriptors from your training pictures, who each one has a probability associated with being a bus, a car, a person, a horse, and so on. And you pull them, you then take another picture and you try and use the bag of words to describe the other picture. And in doing so, you build up a statistical set of probabilities for what is in the picture. You constrain things by geometry. So, for example, you know that the feature that turns out to be the tail of the horse is always to the left or to the right of the head, and you can use geometry to constrain how these features relate to each other. Unfortunately, it's sometimes termed an NP, numerically NP complete problem. So with the more objects you have, you grow at an exponential rate as to the probability of getting a good match. The game at the moment is to develop techniques that scale with to the logarithm of the number of classes that you're trying to work with, rather than n squared classes. People are using deep learning networks to explore these properties simply because you can construct fairly complicated models and assess their probabilities reasonably quickly inside an appropriately organized GPU array. It all comes down to machine learning in the end, and that's something that's outside the scope of this lecture series, but in introducing introducing you to OpenCV, you will appreciate that there's quite a large and growing section on machine learning inside OpenCV. So OpenCV is giving you the tools to extract the features and also the tools to manipulate them in probabilistic ways to build up models and test for those models. Back in 2009, a guy called Hinton developed the restricted Boltzmann machine that has been used since to produce learning machines based upon small statistical changes in the machines as they are taught. It's worth having a look at the deep learning tutorials on those if you're interested in deep learning. Things have moved on reasonably well since Hinton, but at their basis is still networks that behave in the same way as his. So there's a whole load of examples of machine learning in there that are quite interesting, and some of these have been implemented in OpenCV as well, so it's relatively trivial once you've got a matrix of features to pass them into, to construct a training set and then pass them into analyzers. Okay. Now I'm conscious that I've just skimmed along the surface of all of those things. I haven't gone into the maths of any of them, and I think for the purposes of this module, the maths is not so crucial. It's the principles behind them and how you might work with them. So with that in mind, I want to spend the rest of this session getting into some of the OpenCV stuff, so you feel you're mastering OpenCV and then can extend your learning into all of these other areas. So I'll stop there, and what I want to do now is to did I give you this document last week? Okay, I've updated it slightly to include the correct. I missed out a library in this template. I missed out image codecs in the dot profile for Qt. But you can take a break now if you wish, or just plough straight into doing some OpenCV things. I'll come around and make sure you're handling these things, but it's a self-guided tour of OpenCV around the topics that I've covered. Some of the topics have C code that I've provided in the DLE. Some are in the samples page. So if we look here, we've got contours, we've got corner detector, we've got Harris, we've got sub-pixel resolution, which is we've got good features to track, which is the Shear-Tomasi corner detector. It's in parallel with learning OpenCV. It's worth building up a project, for example, around corner detector or Harris, and then running it with a camera, or if you don't want to use a camera, just grab a picture from the internet and run it through here. But of course, according to whether you're using a picture or a live video, means you may have to modify the code to pull the image in from live video or from a static picture on your machine. OK demo is a tracking demonstration, and OpenCV stereo SVM sample, stereo example, stereo calibre, stereo match are what we're going to use with our OWL robot. For those of you who've got cameras, video capture basic is worth trying first of all, so you understand how to open up a camera stream. It's actually made very trivial in OpenCV 3.1, 3.2 and above. You just have to open an input stream, and that input stream can be a camera, or it can be some other device. Read it in, and it will then automatically read frames in from the camera as fast as you want to take them. So generally your code will operate in a loop where it takes a picture in, runs the processing, displays something on the screen, and then goes back to the beginning of the loop again, picks up another picture and keeps on going round and round and round. So have you, I'd like to see you running through the samples in OpenCV, just so you understand what you're doing. Do you have a camera, or you're going to just be using? Okay. What I suggest you do is in here you learn how to create a new project from the Qt PFC document. So create a new project, get the .pro file set correctly, and then open up one of the samples and paste it into the main .cpp of your newly created project, and then work through that slowly, making sure that you can get it. Okay. How are you with software?
Is there things like download?
Yeah, it should. It should say at the bottom, do you want to download the file? Zip it up for you. Sadly you do, but you can cheat if you're not bothered, which is to just have one, create one new one, call it main.cpp, and then open that up and just paste the contents of that into the main, and so you use the same project, but you just do different things with it, which is cheap, but quick. How about you? But how are you with writing C code?
C code wants to write C++. It's Python I've never seen before.
Yes, yeah. I don't think there's not so much difference between C and C++. The painful things are how you can access different parts of so functions can have variables that go with it. So when you create a new function, like a Shin Tomasi good feature, good detect, it will have several parameters to it that you
No,
can
θα βρω
adjust.
γιατί κάτι
The
νομίζω
syntax for
λείπει.
it is good features to track dot and then the variable name. So you can stack things like that. So you can
Void.
have lots of
Αυτό
procedures hidden within one
void λείπει
overarching
έχουμε αρχίσει.
procedure.
Τι κάνουμε το κάνουμε πρέπει να το βρούμε
Unfortunately,
μέσα
C++
στην αρχαία.
programming is lovely and that sort of thing. So it can be a bit painful to read through,
Το
but
contours.
you get used to it in the end. Have you actually been able to run this yet?
No, don't hit run. Is that far in there? Video.
Okay, and this is your track bar.
Τι έλεγες?
So as you change, this is
Είναι
the only
ωραία,
way
θέλω να
you've
το
got
στο
to input
contours τώρα.
in a really easy and quick way from
Το κάνει drag and drop. Ωραία,
Is
δεν έχεις κάνει άλλο, απλά πήγαινε κάτω και κάτω build.
You may have seen
Το
what's
έκανα, δεν μου
doing
βάλε
here.
κάτι.
It's just
Ωραία, τρέχει το.
reduce this in size a little bit, so
Πω, γαμίζει και δεις. Είναι ήταν, σου βάλε τα παράθυρα εδώ.
so that's the input image.
Μαλάκα αυτό τώρα το έκανα πριν compile και δεν μου έκανε
So
κάτι.
something you've got to
Αυτό το κάνεις
understand
compile και μετά να το κάνω μαζί.
is
Τι? Να το κάνεις και compile και run, δεν το κάνει ένα μαζί.
interacting with the
Δεν σε
user.
πιέσα.
Anything that
Πρέπει να το
interacts
κάνεις
with the
build
user,
και μετά run, δεν τα κάνει όλα
is
μαζί.
on
Το κάνα εγώ μόνο build,
in the
δεν το
system
κάνει και run,
domain.
νομίζω θα τα κάνει μαζί. Όχι
So
ρε.
you have to
Όταν το κάνεις run κάνει και build.
schedule the mouse with everything else because this is context dependent. So this track bar only runs in this window. It doesn't run in this window. It only runs in this window. So this program only receives input from the track bar when somebody clicks on the mouse and moves it. So there's software that actually inside the operating system or inside the operating system interface with OpenCV that is providing that interpretation. And so this is called a callback. So you set this up, compile it, and then the operating system calls you back when you click on that.
Okay.
So it will only run this piece of code when you click on that. That piece of code is being tested there. So it won't change. The results of on-track-bar will not change at all unless you clicked on something down here. Because you've associated this track, you've drawn what the track bar is. The track bar is this here, which is what you've drawn here.
Στο διάλογο.
And it's reporting levels.
Λοιπόν,
So it's telling you how many levels, and you can see levels.
εδώ τα φτιάχνει. Source.
This is generating this picture. And this bit is the bit that's interesting. It's finding contours and then making. So it's finding all the contours in this picture. It's He does it to find. No, I don't know. But anyway, for every. Oh, I know. We resize because the number of contours changes according to this.
Okay.
So we approximate each of the contours using a polygon. So you can see these are approximations to that smooth contour. Each of those smooth contours, except for those straight lines, are all approximated by a polygon. And the polygon goes through for every contour it finds. It makes an approximation. And if you look up approximate DP, which you can do in two ways, you can do follow similar with the cursor. That gets you to the commented code itself. So it calculates a contour perimeter or curve length, and there's a value called epsilon, which is how close it's going to bother to map. And you can see that near perfect curve there is being approximated by just straight lines. So changing epsilon will change that. So if we just go back here, we could change that that 3 to be a 5, I think. As soon as it's 3, 5. Stop it and restart it, and we should get. I'll have to read the documentation on all of that. So it's helpful with all of these to have if you type in OpenCV, I think this is 3.1 document. So now we can search for prox. If you type in prox poly, all one word, poly dp, return. So this tells you what it does. There's a link to the algorithm that it's using, and you can also here just say type OpenCV 3.1 prox poly dp, and you've got some examples. Now this is a Python tutorial. Also, you can just remove that one. So this is 2413, 3.1, creating bounding boxes on surface contours. These are different takes on the same thing. Shot knobs and shape detectors. This gives you all of the things that you can use for finding contours, fitting ellipses, doing the Hughes moments that I mentioned the other day, finding out whether the curve is convex or not. So it's that you quickly overwhelm yourself with all of this. And in order to do that, in order to understand what contours are, you have to also find out, you have to look up fine contours. Now, so there's a fair amount to explore in this hour now, just looking at contours and what's DP and understand what's going on here. So you get on and do that. If I just pause it, I'll put a breakpoint there. Let's put a breakpoint there. So this now, it does the trackbar and it's waiting for a key press. So it will just do on the trackbar, and the trackbar does all of the drawing for the contours that have been pre-calculated down here. So that's the reason why changing that to a 5 makes no difference. But this approx poly DP we haven't got to yet. We've just stopped at fine contours, and here we can look at contours more, and you can see here's all the contours it found. It found 62 contours in that picture, and the first contour had 37 points in it, and those are the 37 points. The first one was at 1x1, y366, and the last one was at x2366, and that's closing, that's a small loop, I guess. So we can just continue. Now, because we've continued down to here, we now no longer, because we're doing everything on callback, we no longer have access to the debugger unless I Oh, actually, so if we go down here, I'll put it onto a resize. Sorry, I'm not confusing you. I'm selling in my head now about what's going on. Contours to resize. It's changing the shape of the matrix, because it's just matrix operations. I think it's probably flattening it, so it's come back to it. Alright, but the thing is looking up a function, looking at examples, coming back to here, looking at the code, and just checking things. Contours are just linked lists of points. That's all they are. But they're done in a hierarchical fashion, so if you look up and find contours, you'll see how the hierarchy works. How are you getting on?
I can open this thing called
Right.
I can't open this state.
Okay. So are you okay.
I'm open all the.
If I may just show you what I was telling your colleague here, that let me put a breakpoint there. So I can now run that code. Stop it. And I'll run that code. And this is the input image, which is this. These have created this image, and we've shown it IM show. So this is the show of that image. We then created a list of points, a list of points. This is called contours naught, and we're going to find the contours in here. So if I step through, hold on, I'm not in debug mode. Let me just go into debug mode. So we'll single step into debug mode, and look at if we step over that, we can now, the image that we created, we've found all the contours in it. And here are the contours. There's 63 of them. The first contour, contour 0, has got 37 points in it. The first point is at 1,366 in the picture, that's the X and Y coordinate. The last one is at 2,366, and there's ones in the middle. So this is probably drawing one of those circles. So one of those circles, I don't know where 1366 is going to be. Somewhere there. So you need to look up, find contours and prox polydp to see what is happening in this piece of code. So what we can do is we can go to see the prox polydp example. And here's some examples. If we look here, this is a Python example, but the principle is the same as C. This is about contours and approximating contours. We can go back here, look at OpenCV tutorials. There's examples of a Harris corner detector. I'll just try and see whether script Fourier transform. Yeah, those are all. So this is about contours and bounding boxes in a similar way to the one that we're just playing with. So just by searching you can find lots of useful things. Let's look for find contours. CV 3.1 because we're working with CV 3.1 and we're looking for C++. So that's another example of finding contours. Actually, this is not a very good example because it doesn't tell you anything about it. Let's see whether this is better. No, it's the same way.
بدأ كل المرة اللي عم بصير.
بدنا شي خضر لي.
Ty ganni stress.
Jo, maar zo bedoel ik.
So this is what you need to know about finding contours. This is actually the procedure find contours. It tells you what it does, how you can approximate with it. It should also tell you what algorithm is being used somewhere. Oh yeah, there's the algorithm.
Okay.
132. 132. Topological structures. Now we should also
ούτε αυτό.
Perhaps you want to be going through some of these as well. Let me just go back to fine contours and try and get some. Right. So this, although this is in Python, you'll see that all Python does is to put CV dot in front of the function. Mostly there's a couple of ones where they're slightly different, but this tutorial tells you about contours in a picture. Okay, so have a look through that. And if you've been following, you can check that too. It's a Python tutorial on contours. Are you guys okay?
Yep.
Alright.
Θα ξέρω. Δεν σου δώσεις κάτι.
Cannot open core.
Ξέρω, απλά θα τελειώνω αυτό.
Έχει πάρει το φίλο μας και τον ταντεύει.
Και πέρσι τι έκανε.
Ναι. Άκουγα στο προηγούμενο τέτοιο, στο προηγούμενο βίντεο που δεν μπορούσε να κάνει την κατάσταση ο άλλος και του έλεγε τι είναι αυτό ρε, δουλειά είναι αυτό εδώ.
Εδώ.
Ναι.
Ναι.
Έχεις ένα μαυράκι, πρέπει να το κοιτάξεις αυτό.
Τι είναι το άλλο.
Το βάλεις. Πάμε ένα τσιγάρο.
Κοίτα.
Τι έπαθε, LSD.
Επειδή είναι LED. Ναι, θα βλέπεις.
Oh, okay.
Τέλος. Μισό λίγο. Now. Δεν μπορώ μαζί.
Yeah, yeah.
Okay. Right. Did you put that in manually or did you put that in? I put that in. Right, that's wrong. Oh, actually, yeah. No, what you've done is slightly wrong. Where is that piece of code?
In the product book. go into that existing file.
Okay, so you go there and you click on project. Okay, so this you can. Okay, so then we do different components of it. No, it doesn't, but it works. Sometimes you can be a bit faster than the machine, and you can be doing things.
But I got to this stage and
Right.
what do I do?
Well, now you can run it. So it's here.
Yeah.
It's going to read in an argument from the command line.
Yeah.
Now you didn't know this, but the command line is under the run flag here, is there. So if you type in a full path name of an image, it will find it and then process it.
Okay, cool.
And just going back here, if you put a breakpoint there, you can run it, stop it there, and discover where the source is. Either the source is -1, then it means it couldn't find it.
Okay,
Or
so just think we need to
Yeah, so you just want to make sure that you. So you now have to just find an image and put its full path.
Cool. Okay, thank you.
Project. This is what we need in the project. But I don't have one. You can see the version one.
Yeah, you did say
That's what I found.
you did say that, but I said it earlier.
It's made one now. New project.
If this is too heavy stuff to start with, start with the other tutorials on that are on the on my DLE. But
Yeah.
it's useful stuff. You don't have to understand absolutely everything. You've just got to understand little bits, and then with practice, you'll find out which settings you need.
The two far, okay. I don't want to hold it too far.
Can I remind you to log in on DLE as well, please, to register for this session?
Is that working?
Not that strong. So, I got the community location, down it, put it in the product.
Okay, show me where that is. Go back to debug. Compile program. Build project corners. No, you don't have to do that. But for some reason, the debug.
Molt treball, error. Ok, appunto la serie quanto tempo? Ah, bella da composto.
It could be because of
with you.
This is up to date. Okay. Sono tre che dormi. Poi credo su tre. Ok. No, sono bene.
You were compiling it with a 32-bit code generator. This was the default, but Qt won't be able to parse it, so it won't be able to debug it or anything. So you can do it simply. Yes, select desktop, select that one as make default. I did it on my machine over there the other day, it worked. Did you have Compose 2 work? Yes,
failed. Quindi buono di così. No? Quindi buono. Lógica no sé si consigo dar tudo comigo. Vou confundir. That's okay.
This was not on these pictures, but the same image we use upstairs in the students.
Lógica.
Do that and it runs. So that works. So let's take that. And there. We build the jump. So that works, no problem. Is this something to do with the naming convention of the source? We actually have medical customers. I am. I think that name. Well, anyway, we've got the jump that works. I don't think you should ask too many questions. It's written in Qt. It's written in qtpfc.com. My online help. There. That. It's written in that.
Holy God, man.
Film.
I'm